Good morning, everyone. My name is Benet Eiximeno Franch, and today I will talk to you about our research on live analysis multi-core integration for numerical engineering. So I would like to start my talk with a question, and is why are we going to remember 2024 in BSc? Well, for me, the answer to that is pretty easy, and it's basically because it's the year that we finally got access to our new machine, Mare Nostrum 5. And we were really happy with that because all of a sudden we had access to more than 4,000 of the most expensive and fastest GPUs in the world. And that was an amazing boost for our research because, as one of my friends likes to say, we had unlimited power in our hands. But with that, with our happiness, we also had the sadness of some of our old friends. And those friends are the CPUs that felt a bit alone after that because we only cared about GPUs. Basically, when we run on an ACC node, there are 76 CPUs that are completely discriminated. And they tell us, well, you wouldn't be here if it wasn't for us. You are treating us like rubbish now because you only care about GPUs. And please stop ignoring us because we can still help you a lot if we are not bored like we are right now. And, well, who can save the CPUs from being bored? The answer to that is LAMINE. But I'm not talking about LAMINE Yamal, actually, because our CPUs, unfortunately, are still American, and they don't like soccer a lot. LAMINE, for us, stands for Live Analysis Multi-Core Integration for Numerical Engineering. And, well, the numerical engineering part is because we use the GPUs to numerically solve the aerodynamics of different geometries. Live analysis is because at the same time we're using CPUs to the visualization of this simulation. And the multi-core integration, of course, it's because GPUs and CPUs are working simultaneously to do both tasks. The numerical engineering side, we do it with SOT2D, that is our CFD solver. That solver numerically integrates the Navier-Stokes equations, which describe the motion of any fluid flow. So they are key to design better cars, aircrafts, cities, and wind turbines. And we do that on the GPUs because they are a really big boost for this task. For the same case that took 40 days in Mare Nostrum 4 using our full queue, now we just need 6 days using 32 GPUs of Mare Nostrum 5. Then the live analysis, we do it with PyQuBarC. I'm sorry if you heard PyQuBarC. That was not my intention here. PyQuBarC for us means Python Quick Visualization, Analysis, and Reporting of Simulations. And basically, it's the tool that we execute on the CPUs so that we can convert the boring numbers and letters from the equations to some meaningful videos like the one here. This is an aircraft at takeoff conditions. And basically, thanks to these videos, we can see the interaction of the air between the engines, the wing, and the fuselage, so we can design more efficient aircrafts that help us traveling without damaging the planet. And then finally, we need a brain behind all these operations. This brain is PyComs. PyComs is a library developed by the Workflows and Distributed Computing Group. And basically, it's the one managing the interaction between the SOT2D and the GPUs and PyQuBarC in the CPUs. To do so, PyComs gets us input after how many steps we want to save the visualization. And after that, it launches the job on the CPUs for the visualization tasks without stopping the simulation that is still running on the GPUs. And now that our CPUs are not bored and are happy again, we get massive improvements in disk space usage because, well, if we wanted to save the full case that I was showing before of the aircraft, we would need more than 5 terabytes. But if we do this visualization on runtime and we get only the video that we want to have, we can reduce the disk space to a bit more than 1 terabyte, so we reduce the disk usage the 75%. And also we get a huge improvement on timing because our previous strategy was doing that on ParaView after running the simulation, and actually it runs out of memory when using the full debug queue of the GPP machine. And with LAMINE, we can do it with just 27 seconds after each snapshot is computed. And once we have the contour, we can render it instantaneously if it's small even on a laptop, because the mesh is much smaller than the one we have from the original test case. And well, that's all from my side. Thank you very much for your attention, and also thank you very much to everyone involved in the research.